the hello and welcome to the next podcast, or the first podcast, sorry, in atomic and nuclear physics, looking at the atom from a rather historical point of view, looking at the development of atomic models. It's kind of worthwhile looking at this from an historical point of view because it is a very good illustration of how ideas change in science and how new evidence brings about new ideas, which can revolutionize old ways of looking at things. So we're just going to look at the first two assessment statements of this section today. We'll start with trying to remember what we know, or what we think we already know about an atom. We've already gone through the topic on thermal physics, and one of the things that we looked at in thermal physics was the ideal gas, which gave us a certain number of things about atoms. The idea of the atoms itself came about from the Greeks, from the ancient Greeks, Democritus et al. And that idea hung around until the 1600s, when the development of thermal physics, the precursors, the scientific backing for the Industrial Revolution, caused us to look at things like the behavior of gases in a lot more detail, and to model the behavior of gases and to make predictions based on an ideal gas. And because ideal gases aren't perfect gases, but ideal gases are perfect gases, but real gases match ideal gases, not precisely, but approximately, means that most of their ideas we can hold to be true. And so, coming out of that, we knew that atom was the smallest sort of bit of matter. That was what was thought, at least at the time. We knew it was very small, about 10 to the minus 10 meters, and we knew it contained negative and positive charges. We didn't know much more about that, and that was overall neutral. So this was all evidence for the atom. A little bit of late evidence for the atom. This diagram here shows something called Brownian motion. Brownian motion was explained by Einstein, actually. Brownian motion is where small, tiny, almost microscopic or just microscopic things like grains of pollen or smoke particles are suspended in water or in the air. And if you look at them very carefully under a microscope, you see that they tend to sort of be vibrating, almost moving around from one place to another. And Einstein said that this was because these invisible atoms keep on hitting them, slightly more on one side than on the other side. I mean, it happens to everything, but only in the case of these very, very small but still visible things is it noticeable, and it gives them this sort of jittery motion. So that's what we knew about atomic models. 1897, J.J. Thompson uses this piece of apparatus here to discover the electron. Basically, this was a very exciting time. Röntgen over in Germany was just discovering X-rays, and people had sort of discovered these things called cathode rays. They were called, came from the cathode, the negative end of an evacuated chamber, and when it was charged, and you could make these things visible by putting a phosphorescent sort of background strip on, and you can hear a picture of it in action. And what Thompson did was he realized that these things could be bent by magnetic fields, and he set up a bit more complicated apparatus than this, which had a couple of plates, which enabled him to make some predictions about the properties of these cathode rays. And the postulate, the hypothesis that he made, was that these represented, for the first time, something that was subatomic. From the ancient Greeks onwards, the atom was always thought to be the smallest bit of matter. Now, Thompson was saying, no, there are actually smaller things, electrons, which have a negative charge. So we already knew that matter consisted of positive and negative charges, and now Thompson was saying, well, we've got these little things called negative charge, so where's the positive charge? And what Thompson's model of the atom, is known as the Plum pudding model. Pudding, by the way, this is pudding in the English definition of the word, which means dessert, effectively. Anything you eat after your main course. So plum pudding is a particular type of cakey dessert, a bready dessert, into which is baked plums. Okay, like this. How does this apply to an atomic model? Well, Thompson's atomic model basically says, well, you've got this cloud of positive charge. Embedded within are lots of electrons, negatively charged, which represent the plums. That's the plum pudding model. Okay, now hung around for a few years until these chaps came along. On the right we have Ernest Rutherford, a student of Thompson's in the past, but now working as a professor at the University of Manchester. And he had two graduate students, Hans Geiger, who later went on to develop the Geiger counter, and another Ernest Marsden, and another New Zealander, both of these New Zealanders. This main photograph taken in 1918 or so, so a few years after the development, and this photograph of Marsden taken a lot later when they did their famous experiment. Geiger and Marsden were both only in their early 20s. They were graduate students studying for their doctorate. Now, there's a link on the internet, there's a page, where Chadwick, who was a later contemporary of Rutherford's, describes Rutherford doing what Chadwick calls silly experiments. He said he did lots of silly experiments, which are experiments which seem silly now to us, and maybe at the time, and gave negative results. They were experiments that didn't work, but they were still worth doing, as Chadwick points out, because if it gives a positive result, an unexpected positive result, then your silly experiment can change everything. And that's exactly what Rutherford did in 1909, or what Rutherford had the idea of doing. Rutherford was a brilliant experimentalist and a brilliant intuitive physicist. He had inspiration, he had ideas. But he also wasn't going to sit in a dark room looking at an experiment for a year, so he gave that job to his graduate assistants, to Geiger and Marsden. So what was their experiment? Well, they had to take some of this newly discovered radioactivity stuff, which gave out what we now know as alpha particles. It was actually Rutherford and Geiger who did a lot of work identifying alpha particles later, but they knew some idea of what these things were. They knew they were relatively heavy compared to electrons, particles. So they put these in a lead block with a hole, so sort of a ray of them came out of the block, and they passed them through gold foil. And then they had a screen or a detector. It was actually a little tube with a little strip of this which they could move backwards and forwards along a rail. And when an alpha particle hits this detector, it gives off a tiny, tiny little flash, which you can see very carefully if you're looking at it with the naked eye of a proper detector. But it doesn't happen very often, which is why Geiger and Marsden spent an entire year in the basement of the University of Manchester doing this experiment. Now, why was this a silly idea? Well, because in the plum pudding model of the atom, the alpha particles should just go straight through. No problems. Not deviated left, not deviated right, not bouncing off, just straight through. Because they're much, much bigger and heavier than the electrons, they'll just push them out of the way. And the positive charge was this sort of soft, cloudy, amorphous blob of positive charge, which was Thompson's plum pudding model. So Rutherford's bright, brilliant and silly idea was to test this theory. And indeed, Geiger and Marsden did realise that most of the alpha particles went straight through and hit exactly where they were predicted to hit. However, the key word in that sentence is most, because not all of them did. Some were deflected, and when really pushed by Rutherford to extend the experiments, they discovered that some were actually pushed all the way back. Well, how does this work? Well, to illustrate that, I can use the lap here. Here we have a gun firing alpha particles through a sample. And here is the plum pudding model. So you have a cloud of positive charge with negative charges embedded within it. Turn everything on, click, turn on. And all the alpha particles go whizzing through, no problems, not deviated at all. That's not what they saw. Instead, we can look at the Rutherford atom. And in a Rutherford atom, the alpha particles approach, and yeah, most of them go kind of straight past. Oh, by the way, notice the difference in scale, 150 femtometers compared to 300 picometers. That's an order of, well, 3 orders of magnitude difference. 10 to the minus 12. 300 times 10 to the minus 12 compared to 150 times 10 to the minus 15. But some of the alpha particles are deviated by quite large amounts. And occasionally, if one approaches really center, it's pushed all the way back. Now notice that previously we had a big atom all spread out. Now our electrons are still over here, but we have our nucleus very much concentrated in the middle. Okay, these alpha particles are positively charged, so they're being repelled by this positively charged and much bigger nucleus. We know it's big and heavy because it pushes back the alpha particles. We know it's very small because most of the alpha particles concentrate it, go straight through. It's only the ones that happen to really closely approach the nucleus that get deviated off. So this is the first appearance of this idea of a nucleus. So let's go back to the presentation. So yeah, so there's Rutherford's model. The gold atoms, very thin gold sheet, only a couple of atoms wide. Alpha particles most go straight through, but a very few are deviated by passing close to the nucleus. Now, Bohr. Niels Bohr was actually worked with Rutherford. A very, 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 very different personality. Niels Bohr, Rutherford was the great experimentalist, and Niels Bohr was the great theoretical physicist. You could make an experiment go wrong just by walking into the room. Also noted for being a very celebrated Danish physicist, probably the greatest of Danish physicists so far, and famous for having a house built for him by the Carlsberg Brewery Company, which actually installed a pipe from the factory, which was next door, to the house, so he could have his favourite beer on tap whenever he wanted. Nice. But what was his idea of an atom? Well, Rutherford's model of the atom was just that the nucleus was surrounded by electrons, orbiting just like planets going around the sun. It was a very solar system based model. Bohr kind of expanded on that idea and said, well, yeah, but there's some problems with Rutherford's model. And the main problem is that the atom would lose energy. The electrons would lose energy. As they rotate round, they would emit energy. That's something that comes out of Maxwell's equations. Any accelerating charge, like an electron going around a nucleus, will emit electromagnetic radiation, he was saying. And therefore it would emit all this radiation and collapse to nothingness. I mean, all the empty space, the huge amount of empty space, we'll look at that in more detail in a minute, just would disappear, the electrons would collapse in, and matter would not be stable, not in the form that we know it. So Bohr solved this problem by, well, cheating. He basically said that you could only have certain permissible energy levels. So you couldn't just orbit wherever you want, you could only orbit in certain energy levels. That was Bohr's big idea. There was a bit more evidence for it than that, and we'll look at that evidence a bit later. So let's just look by a bit later, I mean in the next podcast, so one to look forward to. So the size of the atom, let's just go through because we need to know a bit about that. The nucleus is about 10 to the minus 15 meters across. This is a kind of hydrogen atom. Bigger atoms actually more approach 10 to the minus 14, about 10 times bigger, but for a hydrogen atom, or a small atom where the nucleus is just a proton or a few protons, is about 10 to the minus 15 meters, whereas the entire atom is about 10 to the minus 10 meters, as we said at the start of the presentation. That's a difference of 5 orders of magnitude, 10 to the 5. That's quite a difference. To illustrate that difference, here is a football, which I personally placed on the centre spot of a football field. Now here is the football field. Oh, sorry, and the radius of the diameter of a standard size 5 football is, well, the circumference is 68 to 70 centimeters, which makes the diameter about 22 centimeters. So here's a football field, courtesy of Google Maps. Let's zoom out a bit. So here you can see the school and the football field, and zoom out a bit more, and here you can see just in the middle of the school and 2.2 kilometers, 10 to the 5 ratio. So don't forget, our nucleus, the entire mass of the atom basically is concentrated in the football size, in the center spot of the football field, and our electrons, which by the way would have the mass and size of mosquitoes, are about 2.2 kilometers away. The atom being 2.2 kilometers in diameter. So most of an atom, the vast majority of an atom, is empty space. Just to very quickly finish this particular bit of presentation, just to complete our picture of the atom, Chadwick, Mr. Chadwick, there's a photograph of him, who I mentioned earlier. He did some interviews talking about Rutherford. In 1932, he used the equipment you can see there to discover the neutron. It was already known that there was something there, because Rutherford himself looked at alpha particles, as I said, and said, well, it's got a charge of 2, but a mass of 4. So, how does that work? But it was Chadwick himself who really put together what we would now think of as the kind of classical mid-century picture of an atom being a nucleus with protons and neutrons surrounded by orbits of electrons in given energy levels. And that concludes this first podcast in this particular unit. Thank you very much.